So for this final video on total air conditioning, on our total air conditioning case study, we're going to talk about how to apply conservation of mass and conservation of energy to atmospheric air, total air conditioning processes. Now this is going to be just a demonstration. It's not going to cover every scenario, but I find it's best to learn this by doing a problem, which is also our final lesson objective, to actually solve the problem. So let's do it all at once. Now I chose thermal fluids 36.1 as a sample problem. You may not have this, or it may be a different number in your book. That's not important. What's important is the actual problem. So let's take a look at what we have. Known: an air conditioning process with evaporative cooling, which is a special type of humidification, and heating. And those details are very important. They'll come into play very soon, so hold on to that. It wants us to find the following things. It wants us to plot the entire process on a psychrometric chart. It wants us to determine the temperature at state 2 in degrees Celsius, determine the mass flow rate of dry air given a heat transfer rate. That's kind of a clue there on where you should be looking on the problem to solve, where it's easiest. And then determine the mass flow rate of the water spray being added in our evaporative cooling. So let's make some assumptions. Well, we're going to assume in this problem that it's steady flow, because it hasn't stated otherwise, and that's how we've solved our problems thus far. And we're going to assume that the change in kinetic energy and the change in potential energy are negligible, so they're equal to 0 when we do our first law of thermodynamics. So let's start off with part 1. Let's plot the entire process on a psychrometric chart. Now remember, a psychrometric chart is all at one temperature, so I need two other properties in order to fix a state. And it's also important to make sure you're on the right psychrometric chart, you're in the right units. Now this problem up until this point, and all the required answers it wants are in SI, so make sure you're on the SI chart, and we're assuming it's atmospheric pressure of 101.325 kilopascals, or standard atmospheric pressure. So we can't use pressure to fix our states, but let's use the other properties that we know. So let's go to state 1. It tells us the temperature, and that's dry bulb temperature at state 1, is 25 degrees. So let's draw a line up from there. It also tells us that our wet bulb temperature at state 1 is 10 degrees Celsius. So remember, the wet bulb temperature lines are these diagonal dotted lines, and it's indicated here the value at 10 here. You can use the scale on the left or these scales on the lines themselves. Let's draw a line of constant wet bulb temperature. And where those two lines intersect, well, that's state 1. So let's mark that as state 1. Now state 2 is a little bit more complicated. We don't know a lot about state 2, so let's skip it for now. Let's put state 3 on our diagram. So state 3, we know that the dry bulb temperature is 23 degrees Celsius. And we don't know the wet bulb temperature, but what we do know is the relative humidity. It tells us the relative humidity is 40%. Remember, these curved lines fanning out are relative humidities. So here's 40%. I've annotated it on my graph. And where those 2 points intersect, that's state 3. Now, this is where the details come in. How do we go from state 1 to state 2? And then how do we go from state 2 to state 3? And those details are going to help us fix state 2. Now remember, state 1 to state 2 was an evaporative cooling, which is a special type of humidification process where I'm adding water at the adiabatic saturation temperature. And so by doing that, I maintain a constant wet bulb temperature. So I know that I should be cooling using a constant wet bulb temperature. So state 2 is somewhere along the line, on this line of constant wet bulb temperature from state 1. However, I still don't know where along that line is. So let's look at how it goes from state 2 to state 3. From state 2 to state 3, it was just heat. Remember, when we add just heat, we're not changing the mass of the vapor or the mass of the dry air. So my humidity ratio is constant in a heating process. Now, I know you read humidity ratio on this side, but just to keep the graph clean, let's just draw. Remember, these horizontal lines are humidity ratio. Let's draw a humidity ratio. We know it would come from 2 to 3, so let's draw it to the left of 3. And we know that state 2 has to be somewhere along that wet bulb temperature line. So let's draw a humidity ratio of 3, which would be equal to the humidity ratio of 2. And where that line intersects with our line of constant wet bulb temperature from state 1, where those two lines intersect, that's state 2. So it's important to know where you came from and where you went to, and how you did that, what simple processes took place, and understanding how those processes work. So we went from state 1 to state 2, evaporative cooling, which meant we had a constant wet bulb temperature, and then using just heating from 2 to 3, so we have a constant humidity ratio. So now we've plotted that process. So part B asks us to determine the temperature of the atmospheric air between the evaporative cooling process and the heating process. So what is it at state 2? So let's draw a control volume just to make sure we're talking about the same thing, just around this process, right? The key to solving complex, no matter how complex it gets, a complex air conditioning problem is to break it up into small processes to fix and find information. So we're looking at state 2, and we want to determine the temperature. Well, we've already plotted the process from state 1 to state 2 to state 3. So to figure out the temperature at state 2, it's just simply drawing a straight line down from state 2 to our dry bulb temperature. And I read that as 11.6 degrees Celsius. You may read it as 11.5. There's a little bit of leeway there because you're kind of eyeballing on the chart. But 11.5, 11.6, that's close enough. So part C, this is where we're going to start applying conservation of mass and conservation of energy, or the first law of thermodynamics. It wants us to determine the mass flow rate of dry air in kilograms of dry air per second, given a rate of heat transfer. So that's kind of a clue. Now, I know that from state 1 to state 2 to state 3, I'm not changing the dry air, but from 1 to 2, I'm adding vapor. So let's simplify it. Let's just look at this heating process from 2 to 3. So let's draw our control volume there, and let's do our control volume number 2 from 2 to 3. Now in this case, I'm not changing the vapor, I'm not changing the dry air, and that's going to become very important to solving for that dry air. So let's clean everything out of the way. Let's keep the picture. Let's keep part C so we know what we're talking about, and let's work the problem. So let's start off with conservation of mass, and just like I stated, the dry air, we're not adding any dry air, so the mass flow rate of the dry air from 2 to 3 doesn't change. Right? So let's get rid of the subscripts. Let's just call that mass flow rate of dry air. Now, for the vapor, because we've isolated just the heating coil, that heating process, that doesn't change either. So the mass flow rate of the vapor at 2 is equal to the mass flow rate of the vapor at 3. So right now we haven't made much progress, but we're identifying things that are going to help us when we get to the first law. So let's apply the first law, and here's where you're going to see some differences and where you apply the first law to singular substances to a mixture of substances. And we talked about this briefly when we did psychrometrics, so go back to that video if you need a refresher. Because we neglected kinetic and potential energy, we said that the rate of heat transfer from 2 to 3 minus the power from 2 to 3, or the rate of work from 2 to 3, is equal to the mass flow rate of the mixture times the enthalpy of the mixture for 3 minus, that's our exit, minus the inlet mass flow rate times the enthalpy of the mixture at 2. Now, when we defined our mixture enthalpy that we find on the psychrometric chart, that relationship is going to come into play here for a minute. Let's get rid of the work term first, because in this case there is no shaft. Now you may have a problem where there is a shaft, but in this case there is no shaft. So remember, in our control volume, our open system first law of thermodynamics, that heat transfer, or that work from 2 to 3, that power from 2 to 3 is shaft power, so there is none that goes to 0. And using our relationship I just mentioned, the fact that our mass flow rate times the enthalpy of a mixture is equal to the mass flow rate of the dry air times the mixture enthalpy that we get off of our, which is a convenience property that we get off our psychrometric chart, I've substituted those into our equation. Now, conservation of mass. Remember, we said these mass flow rates of dry air are the same, so let's get rid of those subscripts and let's factor that out and say that our mass flow rate of dry air is equal to the change in enthalpy, mixture enthalpy, I should say, from 3 and 2. Now let's just solve for what we're trying to solve for algebraically, the mass flow rate of dry air. So where do we get these values? Well, our rate of heat transfer from 2 to 3, that's given, and our mixture enthalpies, we get off the psychrometric chart. So as long as we can fix those states, we can just quickly draw that data off the chart. So let's go back to the chart. And if I go back to the chart, remember the mixture enthalpy is the scale here on the left-hand side. It's in kilojoules per kilogram of dry air. It's the same scale on this far right side. If I'm this over on this side of the graph, I can use this for convenience, but it's more convenient to use this side. And these diagonal lines, these solid diagonal lines, are lines of constant mixture enthalpy. So if you're on one of those lines, you follow one of the lines up. If you're not, just parallel the nearest line and then just read the values from the chart on the left-hand side. So I'm going to do that from state 2 and from state 3. And I read that as my mixture enthalpy at state 2 is 29.5 kilojoules per kilogram. I put that little bracket in there for dry air to remind myself. That's kilograms of dry air. And then my mixture enthalpy at 3 is 41 kilojoules per kilogram of dry air. And I think you'd agree with that based on those readings. So let's go back to the equation. Let's substitute those values in, and let's double check our units, and remember that a kilowatt is a kilojoule per second, so that'll cancel out the kilowatts. My kilojoules will cancel out. That'll leave me kilograms, and just for brevity I left off the dry air so it would fit on the slide, but that's kilograms of dry air per second, which is exactly what we're looking for, so the units check out. I plug that into my calculator, and I find that the mass flow rate of dry air is equal to 1.91 kilograms of dry air per second, and that's the answer to part C. All right, let's do part D and finish up this problem. So part D wants us to determine the mass flow rate of the water per second, the grams of water per second of the water spray. So let's go back to that first control volume. Let's just look at the evaporative cooling humidification process by itself. So looking at that process, let's do conservation of mass first. Let's clear everything out of the way. Let's keep that picture and the problems so we know what we're talking about. Conservation of mass for the dry air, as stated previously, that doesn't change. From 1 to 2 to 3, I'm only adding moisture. I'm only adding vapor. So the dry air doesn't change, and I just solved for that in the previous problem. So for my dry air, I already know that value for the mass flow rate of dry air from 1. It's equal to 2. It's equal to 3. So let's do conservation of mass now for the water vapor. And you would agree, I think, that because it's steady flow, what goes in has to come out. So the mass flow rate of the vapor at 2 is equal to the sum of what's coming in, the mass flow rate of the vapor coming in at 1, plus whatever we're adding. And we're assuming all of this vaporizes because we're adding it at the adiabatic saturation temperature. So let's write that out. So I chose to use the subscript W because we talked about evaporative cooling in your textbook. The textbook uses W. This problem uses F. In retrospect, I should have used F so it was consistent with the problem, but I was trying to remain true to the book. Just be consistent in your work and know what it is you're trying to solve for. So let's just rearrange and say that the mixture of the water is equal to the mixture of the vapor at 2. The mass flow rate of the water is equal to the mass flow rate of the vapor at 2 minus the mass flow rate of the vapor at 1, just rearranging this equation in this relationship. Now, remember, humidity ratio is your mass flow rate of vapor over your mass flow rate of dry air. So I think you'd agree that I could replace mass flow rate of vapor with humidity ratio times mass flow rate of dry air. If I distributed this through, I would just get mass flow rate of vapor. And that kind of trick is very, very important because I already know the mass flow rate of dry air. I don't know the mass flow rate of the vapor, and that comes in very handy here. And I can get my humidity ratios from my psychrometric chart if I already have those states plotted. So remember, this mass flow rate of dry air and this mass flow rate of the dry air are the same, and they're equal to what I've already solved for. So let's simplify that problem and let's factor that out and say that the mass flow rate of the water spray that I'm adding is equal to the mass flow rate of the dry air in the system times the difference in the humidity ratios of 2 and 1. So where do I get these values? Well, part C, I already got the mass flow rate of dry air in 1 and 2. Like I said, psychrometric chart. So let's go back to the charts. So from the charts, remember, humidity ratio is written here on the right-hand side as these horizontal lines across. So I'm just going to draw a horizontal line from state 1. I read that as a humidity ratio of 1 at state 1 of 1.7 grams of moisture of water vapor per kilogram of dry air. There just wasn't a lot of room to fit that on the slide, but remember, your units are here, grams of moisture per kilogram dry air. For my humidity ratio at state 2, I read that as 7 grams of water vapor per kilogram of dry air. Now we just go back to our equation and we plug them in. So I be consistent with those units. My kilograms of dry air, that cancels out, right? And I'm left with grams of water vapor per second, which is exactly what I'm looking for, is how much feed water I'm feeding back in here, vaporizing in here. Plug those values in my calculator, and I get that the mass flow rate of the water being added for evaporative cooling is 10.12 grams of water vapor per second. And that's it. That's the problem. So I hope that was a good demonstration for you of how to apply conservation of mass and conservation of energy to air conditioning processes. This was limited to evaporative cooling and heating. It doesn't matter what type of complex processes you have, air conditioning process you have. Just break it down into the simple processes and